Hello, good afternoon. This is
Good afternoon, Pritam. So I just have a quick question regarding the recordings. So would we be getting the recordings of yesterday and day before yesterday?
think you will get it. Yes, professor said that to record all the sessions and he will share maybe in the Google Doc. He will
Okay,
share the
thank
link.
you. Sure.
Okay, let's introduce myself. I am Pritam Sen, second semester PhD student, and in this semester I have been working with Dr. Pentelis in American goods. So he asked us to review some basic concepts of linear algebra, probability, and calculus. I think you already attended the 2 sessions of linear algebra and probability. Today I will take recitation on calculus. So basically, I will go through the content of an web page, actually tutorial, and there are so many proofs and many examples and some codes to plot and show some example with data. But I don't want to show all the examples or all the proofs, so I have made a presentation and I will to summarize all the concepts, and I will go through the presentation, and after some time I will show you the web page also. So let me paste the link of the web page here so you can review. Can you see the document? The, the PowerPoint PPT file? Yeah. Okay. So you already know about calculus, you already studied it, and this is actually just reviewing the basic concepts actually that might be helpful for deep learning or data mining related courses like coursework or project purpose. So what is, so you all know that calculus is actually a study of how things change. For example, there are so many attributes. A function is dependent on so many parameters. So we want to change some parameters and see the effect of change the value of function with the change of the each parameter. So there are mainly two branches of calculus. One is called differential calculus and another is integral calculus. So differential calculus actually to uh, divide something into small pieces and check how small change can affect the total thing. And integral calculus is actually opposite of differential calculus. It actually accumulates the small pieces and together it makes the sum. For example, integral calculus is used for to find the area of a curve. So the curve is divided into so many small pieces, and for small pieces we get the area, and it actually sums up to the total area of the shape. And using differential calculus, we can actually calculate the slope of a graph, or if a function depends on many parameters, then we can experiment with each parameter and see the effect. So today we will discuss about differential calculus because it is used in machine learning, deep learning, and other areas. So in differential calculus, we actually change some parameter and want to see the effect. So in machine learning, there is a concept like loss function. Loss function means, for example, a function is dependent on many parameters. For example, let me draw a small graph here, small plot. For example, this is height and this is weight. We collected data from many persons, each one's height and weight, and maybe any other attributes with height, maybe gender, age, many other things. And so we plotted here. So here are some points. So we want to make a curve or make a shape, draw a line actually, draw a line, or it may be linear or it may be a polynomial line. So we actually draw a line so that we can calculate weight for each height. So maybe if I draw a straight line, it may be like this. which tries to fit all the points. So if I draw a line like this, we are getting some error for each values. For example, there is error like this one, this, different kinds of errors. So here loss function is dependent on the height parameter, because height means we actually for this line there are actually two. We think we need two things. One is the slope, another is the intercept. So we call this maybe W0 and W1. Okay, so if we change W0 and W1, we can get different types of loss. And for each lines, we can calculate the loss function. Loss function means how much error we are getting for this parameter. So we can change again W0, W1 and can get different line and calculate loss again. So loss function actually depends on W0 and W1 parameters here. So and we can vary each one parameter and calculate the loss function again. And we want the loss to be minimum for our for genomics, not only for training data, also for test data that we have not checked yet. So we need differentiation for these kinds of evaluation. So let's say function fx, so let's y is equal to function of x. So we want to change some a value of x. For example, we want to add some value with x and we want where's the impact. So for example, we increase the value of x by h. So what's the change? The change is function of x plus h minus function of x. And with respect to the change in x, the we want to measure the we want to actually calculate the ratio, the change and the change in the output and change in the input. The change in the input is output is function of x plus h minus fx, and the change in input is h because we increases the value by h. So if h is very small, then we call that we are calculating the derivative of x. That means with small change of x, we want to calculate the impact. So it is called the derivative of x, which is represented as f prime x like this. And if we want to calculate the value for specific value of x, then it is called f prime a. For example, we want to calculate the value of x f prime x when x is equal to a. This is called f prime a. And if we can calculate the value of the differentiation in a range, for example, from range a to b, then we can call that the x is differentiable from range a to b. So f prime x actually the instantaneous rate of change with respect to x. So as I said before, if we want to change one parameter like w0 w1, then we can calculate the f prime w0 or f prime w1 like that. So different kinds of notation here. We show that the f prime x for differentiation. There are some other notations. For example, we can, as I said, the function is, if the function is, we call the function is y, then we can also say it y prime or ui dx, df dx. There are different kinds of notation, or dfx, dx. This is the parameter for which we are calculating the differentiation. And so there are many kinds of notation, and there are some common functions. We in undergraduate level we actually learned the proofs of this. For example, if we want to calculate the differentiation of a constant value, then it will 0. So and we want to calculate the differentiation of x to the power n, then power comes before and the power will be decreased by 1. And there are some other functions like trigonometric functions, sine, cos, etc. So these are common functions. You don't need to memorize it all. And there are also some rules. For example, there are constant multiple rule. If we multiply a function by constant and get the differentiation value, we just can ignore the constant here. That means we need to calculate the differentiation only of the function, and we can multiply the constant with the differentiation value again. So this is constant multiple rule, and there is some rule. For example, there are two functions of x, and we want to calculate the differentiation of the sum of those functions. Then we can actually calculate the differentiation of each function and then sum them together. And there is also a product rule. For example, two functions are multiplied together. Then if we want to calculate the differentiation, we can follow this rule. First this one and differentiation of another one, then the second one and differentiation of the first one. And there is division rule also. So for division rule, this is the actual formula. So for example, if we want to show an example, for example, this is a function 3x squared plus 2x. So if we want to get the differentiation with respect to x, then first of all we can use the sum rule. That means we want to get the differentiation of this one and this one, and after that we can apply the constant multiple rule. That means we can ignore the 3 and get the differentiation of this one and this one. And so if we calculate the differentiation of this one, that means x square, we can apply the rule here. So 2x to the power 2 minus 1, that means 2x. That means 3 into 2x here. And here x to the power 1, that means 1 x to the power 1 minus 0. 1 minus 1, that means 0. So the result is 3 into 2x plus 2 in 1. So 6 2. So similarly, we can apply the other rules. So these are basic concepts. Now I want to show the partial derivatives. So a function may be dependent on many variables. For example, I showed a graph where the function is dependent on the height variable only. So there may be different variables. For example, height, weight, gender, age, many things. So y is dependent on these kinds of variables. Here x1, x2, and from n variables. Actually, it depends on n variables. Now we want to see the effect of changing only one variable. For example, we want to change the value of x1. I want to see the impact. So we can calculate it using like this. For example, there are many variables here, but we want to change xi only. So we increases the value of xi to xi plus h, and we keep others as same. No change in other parameters. So there is in output there is change. This is the last output and this is the initial value. So the change is that the last minus the previous one, and the change in the input is h. So we have to calculate the differentiation value like this, and h is very small, and we actually present it in this one, the parameter we are changing. So differentiation of y with respect to xi. So there are many other notations like previous, so we can present it like di, dxi, etc. These are showing because different books actually follow different kinds of notations. That's why many notations are shown here. So this is actually partial derivatives, and so there are many parameters here. So we may want to check the definition for each parameter. For example, we can change this one, and we can calculate partial derivatives of all for all parameters. And if we calculate like this and present it in a matrix, then it is called gradient of the vector. For example, x is a vector, and there are different kinds of parameters. Different kinds of parameters means there are actually, as I said before, height, weight, like different attributes. So these are the attributes which we can change. So we can calculate partial derivatives for each parameters. following this rule and present it in a vector. So here the function is differentiated with respect to x1, x2, and xn. So all the results are shown in a vector, and it is called partial derivatives of all, which is called gradients of vector x. So we present the gradients using this symbol delta, and we can show x, or we can ignore it. It actually depends on the notation and other parameters. So, and now I want to show the chain rule. Chain rule means actually a function can be dependent on another function. For example, this is our input. We calculate another, for example, u. U is a function of x. So from x, changing x, we can calculate the values of u. And from u, we y. Y is a function of u. There is chain relation. So ultimately, y is actually dependent on x, because change in x makes change in u, and ultimately it changes the y. So we may want to calculate both. So we can calculate both the effect of u or the effect of x on y. So for example, we want to calculate the effect of u on y. So it will be presented as dy du. That means change in u makes some changes in y. And we may want to calculate the change in u with respect to x. So we can present it like change in u with respect to x. So separately we can calculate this one and this one, x, y. Now if we want to calculate the change in y with respect to x, that means we want to calculate dy dx. We can apply the chain rule. Apply the chain rule means we can first calculate the change in y with to u, and then change in e with respect to x, and then just multiply it like that. So change in y with respect to u and change in u with respect to x. So this is called chain rule. So if there may be many other connections, like the path very long, for example a, b, c. So we can calculate the effect of any other parameter on y like this, like following the chain rule. We just need to calculate the derivatives and multiply all. And we can also apply partial derivatives for this also. For example, x is a vector here. If x is a vector, that means there are many parts here, like x1 to xn. And also, if we apply the function, then the result also contain some parameters like u to um, and ultimately the y, we want to check the value of y with respect to parameters x. So we can apply partial derivatives. For example, we want to make change in x1 and see the effect. So we can actually calculate the effect change in y with respect to the x. So for that, we can apply the chain rule for all. For example, we can check the value change in u1 with respect to xi, and then change in dy with respect to change in y with respect to u1. Like that, applying the partial derivatives and the summation, we can actually calculate all of the change in y with respect to all parameters, all x values. So this example of applying chain rule and partial derivatives. So this is actually preliminary rules. So if I want to review again, these are major branches. This is the concept of differentiation, and these are the notations. and these are the basic rules. And this is actually partial concept of partial derivative, that we can get the effect of each parameter here, and if we combine the all, then we will call it the gradient, and we can apply chain rule so that the effect of multiple functions can be evaluated easily. So if I go through the web page now to show some examples there. In the preliminary section, calculus. I skipped some parts. These are actually some give some examples on integral and differential calculus to calculate the sum of some shape, area of some shapes, and we already show the rules with the differentiation derivatives. And here different kinds of codes are shown using different library. For example, using TensorFlow, we can calculate the derivatives. For example, for this function 3x squared minus 4x, we can define the function and apply this rule. And for small value of a, we can calculate the values of f prime x derivatives. So here it actually implements one function, this function, and this function of x plus h minus function of x into h. And for different values of h, it actually calculates this value. So it presents this value like this. For it actually changes h, and if we make this smaller, then the value actually gets more accurate. These are the notations and the rules and the functions. Here they actually show a plot. For example, this is a plot of a equation, a polynomial equation, and if we get tangent line here, and we can calculate the value of change in this function at this value. So this is calculated in two ways, using the plot and the visualize it, and also it can be calculated using the equations. So we already checked the partial derivatives, and then we show the chain rules. This is the preliminaries, and then we want to check the next concept, single variable calculus and multivariate calculus. So for single variable calculus, the maximum rules shown in preliminaries are applied. So here different kinds of plots are shown, like for example sin x, straight lines, and it actually plots and calculates different kinds of derivatives. So these are the common derivatives. These are actually the same rules for constant 0. For this is actually a multiple rule, same rules. So we will actually skip this part. Single variable actually same as the preliminaries. So there are some proofs. We don't want to go through this. Actually, one is actually needed for us. This is actually linear approximation. For example, I will show the slide again. Okay. There is one rule called linear approximation. In the web page, the proofs are shown. So I just skip the proofs to show the mainly the formula, mainly the concept. So if I add a small value of a small value with the x, then we can approximate it is like that. For example, there is a function of x. We want to apply some change with this value. Then it can be approximated the function itself and the derivative of the function and the change is multiplied with it. So in the web page, the proofs are shown, but I think if the proof is not needed for us, we only know the concept. We also need to know the concept. So if we want to apply some changes and want to see the output, we just need to add the derivatives multiplied with the change with the trivial function. So this is needed actually multivariate calculus. So the rules are shown here. Okay. So as I said, in deep learning, there is concept of loss function and weight. So for example, for linear line, we show that there are two weights. One is slope and another is intercept. For polynomial functions, there are many weights. For example, we have a weight vector with n parameters, w1 to wn. And for a training data set, we are getting a loss function. For this set of weights, we are getting a loss, and which is presented as LW, loss. This is actually loss function. So we want to make some changes in each parameter, each weight parameter, and want to see the effect. So if we make some change in W1, that means we want to calculate this actually. All other parameters are only W1 is changed. So following the rule shown here in this page, we can write it as the previous function, that means the actual loss without the change, the differentiation of the derivative of the function, the derivative of the loss function multiplied with the change here, multiplied with the change in W1. So this rule can be applied in case of higher dimensional functions. So for polynomial functions, we can apply the rule to see the change in loss function for some change in one parameter, like that. We can use the previous loss function and multiply the change with the derivative of the previous loss function. Okay, so we may want to change not only W1, we may want to change all other parameters. So if we want to make change in all parameters, this one, W1 is increased by value, W is increased by value, and all parameters are increased by some different kinds of values, small values. So in that case, we can follow the same rule. So we can keep the previous function and this change and multiply it with the derivative of the loss function. So if we accumulate all, we can present it as a sum of all of these changes. That means change the derivative multiplied with each change, and we will just sum all of this together. So we can apply this rule for single variable like this, and for multiple variable we are actually here other things are added. So if we add all of these things, we present it like this, summation of all the additional parameters. So we can present it in vector form. W is already a vector. W is a vector here. If we show all the changes as a vector epsilon here. And as I said, these are all partial derivatives. Partial derivative with respect to W1, partial derivative with respect to W2. So if show all the partial derivatives vector, we will call it gradient. All the partial vectors in a vector is called gradient. So here all the partial derivatives in a vector. So this is gradient of loss function. Derivative of loss function with respect to W2 all. So this should be actually W1, Wn. So the whole equation can be presented as this simpler form. Loss function weight plus error or the change, the previous loss function, the vector and the gradient. This is actually dot product and the change. Okay, so in deep learning there is another concept which is called gradient descent. So as I said, for example, this is a total loss function for some initial value of W. For example, if we choose W here, the loss is, the cost or loss is this value for this W. So actually want to get the minimum loss value. So first of all, we don't know which should we increase the W or decrease the W. And if we consider 3D plot like this, here the function is dependent on two parameters. In that case, for example, some pair of θ1 or θ2, the loss is here. And this is the total loss function for all pairs of weights. So we want to get to the minimum value of loss. So first of all, we don't know in which direction should we change. Should we change θ1 or θ2? In this case, should we change W in which direction? So, and our target is to get the minimum loss. So first of all, we actually use some initial parameter, initial value of W. For example, this one. This is actually random value. And for 2D, two-dimensional, we select some pair, maybe θ1, θ2. This is actually our initial weights. Then we calculate loss value for that weight, that selection. After that, we actually need to find a direction that makes most changes in W, and we calculate apply the change in W and calculate the loss function again. We continue to repeat the same process again and again until we make the loss minimum. For example, if we increase the W here, for example, if we decrease the W value here, W weight, so it will increase the loss. So we'll understand that we cannot go to this direction. Then we can change the direction and increase the value of W, and it changes the loss again. So we continue to follow the same step, increase the value of W and check the loss function again and again until we get to the minimum point. For this also, we can change each one and check the loss function and adjust it. So the steps are, we choose initial parameter, then we need to find that direction where the L decreases, and then we can make small steps to change the value of weight parameters, and we repeat the whole process. So we already show the loss function here. The loss function is this one. So as I said, this is actually dot product. So dot product, if we know that A dot B, if A is a vector, B is a vector, and magnitude of A, magnitude of B, cosine of L between A and B. So this equation can be presented as magnitude of V, magnitude of the gradient, and cosine of the angle. So for convenience, if we consider the direction, magnitude of direction as 1, so it is 1. So the whole equation is like that. The loss function, the magnitude of gradient of loss function, and multiplied with the cosine. So we want to make the steepest change. That means we want to make the cos theta minimum, so that the loss function is minimum, loss value is minimum. So it will be minimum at theta is equal to 180 degree. Cos theta is equal to -1. So at that direction, the cos theta will be -1, then the equation will be the loss function minus the magnitude. So the change here with the loss function is the gradient of loss is a change. Change means it actually. So the steps will be now the initial parameters weight. We need to calculate the gradient here, and we are actually using theta is equal to 180 and the direction is 1. So we just calculate the weight as the weight vector, the changing gradient like that, and we continue the whole process until this value, the loss function, is minimum. So at that point, we found some weight and we can use this for the model, the machine learning model. So this gradient is we already showed the rule here. We can calculate the derivative for each state, and for multivariate function, we can also use this one, use this chain rule. For example, this is a deep neural network. Here, these are the inputs. This is the input and function. This is actually function output. So these all are intermediate nodes, and each intermediate there is an activation function which actually uses those input and calculates some output here, and it is input of another node, and there is another activation function which calculates the output for this node, and ultimately we get the final output. So for this deep neural network, for example, this activation function are like this. This node is a parameter, and there the input of A is W, X, Y, Z, and these are examples. For example, this is the activation function of this node is sum all of this and calculate the square value. And for this node, this is the equation. It's another formula. For this node, the inputs are output of A and output of B. It just calculate the square value. And for this node, input are A and B. It gets the difference and gets the square value. And the final output is a function of U and V. So if these are actually many relation, and if we want to present the frequency of f w, the input are actually w f z, will be a very function because function of uv. So in place of u, a plus b square, in place of v, a minus b square. In place of, for each a, replace it with 2, and for b, we will replace with this. So ultimately the equation will be very large. And if we are to make change in w and want to calculate the impact in f, we can calculate it like this: partial derivative of function f with respect to w. So if we calculate the derivative, the equation will be very, very large. So this process is very complex for computer to calculate all of this. And if for complex relation, it is not feasible. So we need to apply the rule. For example, we don't need to calculate the change of w, change in f with respect to w in one step. We can calculate the each change, and apply the chain rule to get the resultant change here. For example, we want to make some change in a and to see the result, change in result in f. So there are two paths actually. If I change in a, it will make impact on f in two paths: a to u, a to u to f. This is one path. Path is a to b to f, a to b to f. So now we want to calculate the impact of a. That means partial derivative of f with respect to a. That means we need to calculate this one and add this together. So we already show it in chain rule section. We can use the same formula here. So this, for the change, if we apply chain rule, it will be change in f with respect to u and change in u with respect to a. So for this path, and for this path, it will be change in f with respect to v and change in v with respect to a. So we can calculate these two, this one and this one, and sum it there. Change in function a for change in function a, f with respect to u, and change in u with respect to a, and same this for these two paths. So for multivariate condition, we can also apply the similar kind of chain rules. And if we want to check another example, for example, this is another neural network. So we want to see the change in f with respect to y. So there are two paths here. No, three paths. Y to u, u to a to f. Y to u, a to f. So for this one, it will be change in f for a, change in a for e, change in u for y following this path. Then the path is y to u, u to f. So change in f for u, change in u for y. Another path is this one, y to v, v to b, v to f. So change in f for b, change in b for f, v, change in v for u. So we all we get the sum of all these paths, and ultimately we can get the value change in the impact of y on f, function f. Okay, so I want to review once again from this part, differential calculus. We without in the web page, the proofs are showed. We actually show that if we change some parameter in x, then it will be the previous function and the derivative of the previous function multiplied by the change. This is for small value of the change. And we can use this concept for higher dimensional differentiator. For example, the weight, there are some multiple parameters and we want to change one parameter only. So in that case, we can change only one parameter, and this will be approximated as the main loss function, the differentiation of the loss function, and multiplied by the change. And if we make change in all the parameters, in that case, the main loss function, the differentiation, the loss function with respect to each parameter, and multiply it with the each change. So in vectorized form, we can present it like this: the loss function, the change vector with dot product with the gradient, because partial differentiation of all parameters is called gradient. Then we show the gradient descent for machine learning. Initially, we choose a initial parameter for weights and then calculate the loss. Then we make change in the weight and calculate the loss again, and we go to a direction so that we can minimize the loss. So we continue to repeating the same steps again and again until we get the minimum loss here. This is gradient descent. And here the steps are shown again with the theta is considered at 180, so we can get the steepest descent. And multivariate chain rule is in neural network, each function can be dependent on other parameters, and there are many paths. We can calculate the impact of each change following the chain rule. Calculate in direct matter is very complex, so we can apply chain rule for each path, each component, and sum them together. Okay, so next concept is backpropagation algorithm. So for a neural network like this, we can change each parameter, and there will be ultimately it will change the main output here. So we can calculate the impact of each like this one. So here we can calculate the loss here. This is the output, and we already know the expected outputs for our training data. For example, these are our training data. We get some output. We already know the actual output for this input set. So we can calculate the loss this input, and we found some loss. So the loss actually occurred because of parameters in these nodes. So we can change the parameters in these nodes. So in the loss, there is impact of each node. So each parameters in each node. So we can change the each node and calculate the loss function again. So this is actually calculated using backpropagation algorithm. So the loss function is propagated in backward direction, and we check the impact of each node here. We make changes in each node and calculate the loss function here. So we don't just make changes here and calculate loss again and again. This is not feasible. If we want to make change again and again, we cannot go to the right direction. So here we actually propagate the loss in backward direction and calculate the impact of change in all nodes and calculate the loss again. Change the parameters here and calculate again. So here for output f, we can calculate the change in f with respect to this one, this one, this one. This is actually, and we can following this rule. This rules, the chain rules. For example, for f w, there are two paths. W a u. If we ignore this part, then there are two parts, WAF, WBF. So this is the chain rule for this. Change in F with respect to A, change in A with respect to W, change in F with respect to B, change in B with respect to W. Like that, we can calculate the impact of each one and propagate it backwards. So the loss will be propagated. So for the loss, there is those parameters are related actually for this loss. So for each loss, we can pass loss function and change the parameters of each node. Now we can go through the web page again for these parts. Here the proofs are shown. I just skipped those proofs. First it changes in W1, then it changes in W1 and W2, and it gets this equation, and as these changes are very small, we can ignore this part. So ultimately it becomes this. And if we continue changing more parameters, we can calculate the sum of all changes here. In the vectorized form, here there is an example of shown. This is a function for two parameters, x and y. So if we calculate the gradient, that means we differentiated it with respect to x and with respect to y. So the gradient is like this. Function of f differentiated with respect to x and with respect to y. And for some point, for example, x is equal to 0 and y is equal to log 2, we can calculate all fxy and the gradient by putting these values here in place of x and y. So if we change the value For example, we increases it by epsilon 1 and we increases this value by epsilon 2. In that case, the output will be following this equation. The previous function, that means log 3, without change. The change into gradient. Change into gradient. So this is an example showing the this formula, using this formula. So for this formula and this equation, they actually make some plots and get the approximated values. This is the original function x log e to the power x e to the power y, log e to the power x e to the power y. This is the gradient. Gradient is this one. So it calculates the approximate value for x is equal to 0, y is equal to log 2, and it calculates the true value. And it shows that both are almost same. That means we can use this equation to approximate the change. So this is a gradient descent concept. We set initial change in W and check once again to minimize loss. Here another example is shown. Then the chain rules for a neural network like this one. These are the activation functions. And they try to calculate impact of each parameter following many steps. I skip these parts because these are this actually comes to very complex equations which are not needed. We can just follow the chain rule here. So ultimately they show that the chain rule is applied and they can get the similar result here. And the backpropagation example, as I said, we can calculate the result following this direction or that direction. So they actually showed both. They calculate the impact of A with respect to then A, this one, then this one. They calculate in this way, and also they show the backward direction. They implemented in TensorFlow and other frameworks, using other frameworks, and show that in both ways the results are same. In forward direction and in backward direction. Both are actually same. Second one is easier. The first and forward direction is there are so many complicated equations, but in the backward direction, this is very simple. And there are some actually built-in method in TensorFlow and other frameworks, so we can just calculate using this method. Okay, one more remaining concept is Hessian. It is actually for second order, multiple order, higher order derivatives. Now we only calculate first order derivative. That means we calculate change in f with respect to w. We can want to calculate once again. That means we can differentiate it again with respect to w. In this case, this is presented as second derivative. That means function is differentiated with respect to w twice. So if there is a function of depends on multiple variables from x1 to xn, we can calculate the second order derivatives like this. This is order derivative, and if we differentiate again, this is second order derivative. And we can also combine two parameters. For example, first we differentiate with one parameter, then we differentiate the result with respect to different parameters. So this is j. So we can present it as second order derivative, but the parameters are different. So in some cases, this second order or higher order differentiatives are needed. So if we calculate all the results, all the pairs, here x1 to xn, we can calculate in show in a matrix. In that case, we call this matrix a Hessian. It sometimes is needed in deep learning concept algorithms. It is sometimes needed. So there is actually a library to calculate this Hessian function, Hessian vector matrix for function, for a given function. So if these are the parameters x1 to xn, in this row we first we differentiated with respect to x1 to xn, and we differentiate again with respect to x1. And in this row, in the last row, first we differentiate all with respect to x1 to xn, then we differentiate again with respect to xn. All of this, and in this other rows we differentiated with x2, x3, like that. So if we present it in a matrix form, this is called Hessian matrix. So as we showed before, the function can be approached like this using Hessian matrix. For example, we want to calculate the function x. If we know initial value at some point, we can get the gradient at that point, and we also calculate the Hessian matrix. So we can, like that, we can, from these values, that means we know value of function x at some point, and from these values we can actually calculate the function, the original function. For example, we already know Hessian matrix like H. We already know the gradient matrix, but we don't know the original matrix. The original function. We don't know the function, but we know its gradient and we know its Hessian matrix. And if we know the value of function x at some value of x, for example x0, from these three we can calculate the original function. That's why sometimes this Hessian matrix is needed. The proof is shown in the web page, but I just want to show you the basic idea. If we know this gradient and Hessian matrix and the value of a function at some point, we can find out the original function from these three. So that sometimes Hessian matrix is needed. So here the concept of Hessian matrix is shown. There is one example that actually proves the equation. But there is a function of 2 parameters. Then we know the value of function at 0, 0. We can calculate the gradient at 0, 0. First we calculate the gradient and then we put 0 for x1 and x2. Then we can calculate the Hessian matrix also for that function at 0, 0. First we calculate the Hessian matrix and then put x1 and x2. Then the function can be presented as function of 0, the reference point, gradient at the reference point, Hessian matrix at the reference point, and we multiply with the x factor. So ultimately it will give us the original function, or you can get the original polynomial. So here is another example. 2 examples are shown here, proving this equation. This is also shown as using some plots in TensorFlow, plots the equations and show that it can be approximated like that. So for matrix, concepts are actually same. If this is a vector, we can get partial derivative for each parameter like this. So for each partial derivative, if we present it as some beta 1 to beta n, this is another vector, the derivative vector. This is actually the gradient of x. So these are some basic rules, and we can get differentiation of the matrix from these rules. We don't need to memorize it, we just need to sometimes we need to apply these rules. That's why these are presented here all together. So just review it once. The exercises to plot all of this. So these are the basic concepts of calculus. That's all for today. Today we show the concept of derivatives and chain rules, the basic rules. Then we also check the the differential calculus, and for higher dimension, differential calculus for higher dimension, then the gradient descent and backpropagation and Hessian matrix, but and one use case of Hessian matrix. That's all for today. Any question or any feedback? Okay. Okay, then I think all the links will be uploaded. I will ask Professor to upload it. Okay, thank you all.
Thank you.
Thank you for your time. Bye.
Okay, bye.